The last talk in this session will be given by Gerard van Belle, and Gerard will be talking about a uniquely capable yet simple optical interferometer for ultra high resolution astronomy from the lunar surface. Gerard, you have 15 minutes. I will be warning you in 5 and 2. Thanks.
Very good. Thanks for the introduction, Slava. It's been a long time. Good to see you. We'll advance from the title slide to the first thing, which is we're going to talk about the interferometry problem to get started. Next slide. Without actually dwelling on the problem, I do want to start with the interferometry opportunity, which is if you think about astrophysics, astrophysics has always been advanced by improvements in spatial resolution. You know, we saw the heart on Pluto when we got better spatial resolution because we put a camera right next to Pluto. And that told us a lot about the geophysical history and dynamic activity of the outer solar system. But on many distance scales, that is true. And so there are many things that we want to look at very high resolution. But next slide. We are limited because of what we can do with single aperture telescopes. You need interferometry to get to the highest levels of angular resolution here. So moving to the upper right, you're getting into milliarc second and then microarc second regimes for if you want to image these objects that are both nearby, such as white dwarfs, and far away, such as quasar broadline regions. When I talk about white dwarf and planet imaging, I'm not talking about seeing a dot on the sky. I'm talking about being able to see a disk, see continents, and see seasonal changes on planets, and other interesting things such as the similar sorts of angular scale activity that you might see with a supernova expanding out at M31. And so this needs interferometry, and this is something that is important. So next slide. If we think about what's happening inside of a telescope, what is happening is path length control. You have rays that enter a telescope and bounce around and get to the back end, and they're all bouncing around in an optical telescope through path lengths that are equal across the whole face of the aperture down to about 10 or 20 nanometers. Next slide. Smart people have realized that you can actually still satisfy this condition with a telescope that you have chopped into pieces. A good example of this is Keck with 36 1.8 meters hexagonal segments. And you still have the path length condition being satisfied. With optical interferometry, next slide, what we've done is actually just taken this step one step further. Each segment is now turned into an individual aperture, but you're still satisfying this path length condition. And we do this from ground-based observatories. And that's kind of amazing if you look at the next slide, because over top of each one of your segments, you have the atmosphere bouncing around at 1 to 10 micron scales every 1 to 10 milliseconds. And that's basically about a factor of 100 to 1,000 times bigger than you can allow if you're trying to control this path length condition and get interferometry to work. But nonetheless, if you can actually do all of your work within those 1 to 10 millisecond time slices and control path length and accommodate for these errors, you can actually still get things to work. Next slide. What this looks like in a big telescope, this is from a 4-meter class telescope in very high-speed frames, is images dancing around and speckles smeared across the face of the image. You should actually get a much tighter diffraction spike out of this, but the atmosphere is really your enemy. Next slide. Nonetheless, we do persist with ground-based facilities. A good example of a distributed optical telescope is the Navy Precision Optical Interferometer. In fact, that's where I'm seated right now. And we have baselines out to 430 meters. And we have up to 6 telescopes we use at one time. Each one of these telescopes currently is about 5 inches in size, so quite small. And since we have to do all of our work inside of 1 to 2 milliseconds to track out the atmospheric distortions, we're currently limited to objects that are about naked eye, about a visual magnitude of about 5. We are adding bigger telescopes, so that's really only going to take us up to about a magnitude of 8 or 9, and that's because the atmosphere just kills you. And so we've been thinking about space-based applications, which, next slide. Naturalist has us thinking about potentially a lunar interferometer, and we would like to start off with really a kind of a small-scale demonstration, which of course would lead to bigger things, but really starting with a modest implementation to demonstrate the power of the technique. And so, next slide. The idea that we have here is there are surface benefits for interferometry. Namely, there is a vacuum environment. There's no problems with an atmospheric coherence time of moving things around fast for you. In fact, there's also no problems if you want to look at a bright object to phase your interferometer next to a faint object. You actually have a very wide angle over which you can do this. In fact, it's really limited by optomechanical considerations rather than the atmosphere. The Earth's atmosphere limits this technique to about an arc second on the sky. You also have very easy beam transport since your vacuum comes for free. Out at the endpoint interferometer, we have a giant array of vacuum systems here to transport the beam, which doesn't have any need to have on a surface interferometer. You just basically relay from mirror to mirror and you're already good. This also means that you can go to much shorter wavelengths because you don't have the atmospheric cutoff at about 30, 50 angstroms. It's also relatively stable. I'll talk about this in more detail in a couple slides, but basically vibrationally, it's pretty quiet with regards to what you need for an interferometer. The rotation rate of the moon is, once every month rather than once a day, and so it's about 600 times slower. And so very long baselines are very possible with a stable platform relative to what you can do with a free flyer spacecraft trying to implement the same kind of thing as a interferometer. Next slide. There are challenges of the lunar surface, of course. There's the dirty environment. There's a lot of dust. If you do have a fixed station set up relative to, say, a free-flying spacecraft, you have limitations in the coverage on the sky, and there are mitigations to that. There's also infrastructure problems as far as power and the thermal complications of the day-night cycle, but these things have been accommodated, and people are thinking a lot about these things. There's been a lot of talks already on things like power during this workshop, so I think that there's a lot of smart ideas on how to address that. Kind of the canonical idea, next slide, for a lunar suitcase science that comes to mind when I think of this kind of thing is the UV telescope that flew on Apollo 16. This is a very small telescope, about a 3-inch telescope. Operated at fairly short wavelengths. And this, of course, was the 60s, so they did not have really electronic detectors to run with here, but these were film frames that were used on Apollo 16. And so in my mind, this is kind of the prototypical lunar suitcase observatory. And just stepping this one step further onto the next slide, kind of my thinking is we just have a suitcase and 2 carry-ons. So you have the 2 carry-ons are very simple outboard stations that basically have small 2-inch fold flats that could be steered to reflect the light to a miniature beam combiner at the center that takes care of optical delay and then also beam recombination and sensing. And the idea here is to, again, just demonstrate on the surface with very, very simple instrumentation that you can get pretty remarkable results out of an optical interferometer. Next slide. The vibration environment, I promised I was going to come back to. Basically, for doing very simple interferometric imaging, not anything complicated like astrometry or nulling or anything like that, but just simple imaging, you have to track to roughly lambda by 10. And if you are taking advantage of the UV accessibility from the vacuum environment, if you're going to start with working down to about 300 nanometers, you have basically a need to track down to about 30 nanometers. Apparently the background vibration level as studied on the moon is in general on the order of about 25 nanometers. So that's right at the edge of that. You do get major moonquakes apparently about every week. You get millimeter to 10 millimeter scale displacements, but these sorts of things you can probably basically just throw away the data for that. Maybe the more critical thing that apparently is in the literature is apparently micrometeorite hits. There's a question on what the rate is, but possibly critical events every 10 seconds. But overall, the quiescent rate does appear to be at the level of what you need for interferometry, which is on the order of a few tens of nanometers. Next slide. If you really have to work with a much more dirty vibrational environment, you can always go with an architecture where you have a faint science beam accompanied by a bright tracking channel. And this is really opened up by the fact, again, of the vacuum environment. You can basically put 2 interferometers on top of each other and have a very wide acceptance angle. 1 degree acceptance angle gets you basically full sky coverage for naked eye objects, and you can basically track everything at about 10 to 100 hertz. But overall, either with a tracking channel or if the vibrational environment is a bit more benign, you should easily get to 1 hour exposures on your science channel. And what that means is that a 2-inch aperture can beat an 8-meter telescope of a ground-based interferometer because of the fact that you're not working with a 1 millisecond integration time. You have a 1 hour integration time, and the integration time really, really wins you big here. Next slide. Some other considerations that would come into placement of these sorts of things and the logistics of a suitcase science implementation of an optical interferometer would be you'd want to lay out the outboard stations on roughly a 100-meter baseline. The beam combiner would have about 1 meter of delay line range. And so you would get all sky targets for about 7 hours a month. Targets at the north you'd be able to do all month long. The placement does not have to be very precise, basically consistent with a astronaut being able to plop things down with maybe a piece of string guiding them or something like that. And you can actually, with the small apertures, you can enclose your optical elements with windows so that you don't have dust getting inside the active optics and the actuated things. By the way, the vibrational environment is not just necessarily a bug, but a feature. You can actually fringe track and find out interesting geophysical information of the surface. We had the Palomar interferometer out that tracked through a major earthquake back in 1999, provided some very interesting information on a magnitude 7 event that was 100 miles away. So the fact that we can make ground-based interferometers work here on the Earth tells me that pretty simple setup on the lunar surface can actually take care of can handle a lot of things that the environment will throw its way. I'm confident that we can package this sort of thing into a suitcase sort of enclosure because of next slide. Some work I've already been doing with some partners. Next slide. We've been working on a implementation of this for a free flyer we called Optimas. We're working with my colleagues over at Redwire Space, doing in-space manufacture. This would be basically an ESPA class launch. Go to the next slide. That goes up very small, and then you use in-space 3D manufacturing to get beams up to about 20 meters in length. And basically, a small mission that's kind of a rideshare class that would show a in-space application. So towards that end, next slide, leveraging stuff like in-space manufacture, which already exists. Next slide. We've actually gone from an idea of a fairly small beam combiner here and have some NASA SBIR funding. Next slide. To actually build up this prototype combiner. This was supposed to have been done in an optical lab, but because of COVID last year, I did this at home, taking over my kids' playroom and building up the interferometer on a plastic picnic table, which I think is probably representative of a dirty vibrational environment, both for a spacecraft or the lunar surface. And that gave way to the next slide, where after a few months of building up with off-the-shelf parts, we were able to then put light into this beam combiner. And next slide.
2 minutes.
Thank you. Be able to show that you can pretty easily get fringes off of this system. An important element of what we were working towards as well, in addition to a small portable beam combiner, next slide, was accommodating the fact that the outboard optics on a free flyer with manufactured booms are going to move around quite a bit, on the order of, say, 10 to 100 millimeters on timescales of, say, tens of seconds. And so accommodating motion of the outboard optics in a lunar environment are actually pretty trivial in the face of much more challenging environment we were thinking about with a free flyer. Next slide. So our results from that were that you can actually build a pretty small combiner. In this case, it was about 0.5 meter by 0.5 meter by about 150 millimeter size. And this was all off-the-shelf parts, which you could probably optimize quite a bit for size and weight, and that you can track the outboard optics very easily. You can locate them. And so all this is pretty well suited for suitcase science, we think. Next slide. So the basic idea here would be a 100-meter baseline that would give you 150 micro-arcsecond modeling resolution on a system, and very small mirrors, 2-inch mirrors, but that gets you down to almost a limiting magnitude of about an hour of 19 in an hour. And we feel like you can actually readily test this in a flight-like condition, basically put this into vacuum, and also test on sky with bright sources here that would be representative of tracking on sky. So with that, that's the end of the talk. So thank you very much. I'll take any questions. Next slide.
Gerard, thank you very much for a very enlightening talk about putting an interferometer on the moon. I think this is extremely exciting. So,
thanks, Slava.
Are there any questions, Gerard? Maybe let me ask you a question. Have you thought about the data rate that you would need to have to enable the data transmission down to the ground?
So the data rate's pretty modest. I mean, a good example is the Palomar interferometer, which was a simple 2-aperture interferometer. We produced about a CD-ROM of data per night, and so that's not a huge amount. You do quite a bit of averaging down to smaller data frames with a ground-based facility, and in fact, you wouldn't even have as high of a data rate since you'd be working much slower with the much quieter environment there.
Excellent. And what is the estimated mass for this payload?
So we're targeting something that broadly fits into these restrictions of suitcase science. So each element being no more than 50 kilograms. And in fact, that would probably just be the combiner, with the two carry-ons, the outboard optics, being much, much smaller. Those would just basically have to have some housekeeping functionality for steering 2-inch mirrors, and everything else is handled by the central beam combiner.
Excellent, Gerard. Thank you very much. So let us move on with the agenda.